How on earth can we expect an AI to synthesize complex material science when, honestly, standard monolithic systems struggle to even keep their basic facts straight? Welcome to today's Explainer. We've got some massive AI news to cover today. We're digging into a fascinating recent research paper that introduces a framework known as AlphaAgent. Basically, it's about decoupling retrieval and generation using explicit skill contracts, and it is completely setting a new standard for literature analysis in highly complex fields.
But to really get the solution, we kind of have to understand the problem first. So what is the fatal flaw in current monolithic retrieval augmented generation, or RAG, systems? Two words: context overflow. That and hallucinated links. You see, it's literally like asking one person to hunt down the ingredients, write a recipe, and cook a Michelin star meal all at the exact same time. The system just collapses under the weight of it all. When you ask an AI architecture to search for info, read complex documents, and write a synthesized answer in one go, it gets confused. It tries to reconcile conflicting experimental conditions, or worse, it just fabricates mechanistic links to fill in the gaps.
Okay, here is the roadmap for this explainer. We're going to cover 1. The monolithic RAG problem. 2. Enter AlphaAgent. 3. The retrieval skill. 4. The generation skill. 5. Beating the baselines. And 6. The architectural takeaway.
Part 1. The monolithic RAG problem. Context overflow. Let's see exactly why classic single-prompt architectures break down when the data gets tough.
This completely illustrates the paradigm shift we're talking about. On one side, you have traditional monolithic RAG. It's essentially a messy assembly line where a single model tries to do everything in a single pass. It retrieves, then generates, and that leads directly to context overflow and retrieval noise. But on the other side, we have decoupled skill contracts. By partitioning the workflow into highly specialized agents with explicit input and output boundaries, the system is forced to ensure strict evidence validation at every single step. The researchers hit the nail on the head here. They point out that without external grounding, general-purpose LLMs may produce factually unsupported statements. And why is that such a big deal here? Because in material science, the terminology is insanely context-dependent. A term for a phase name in one alloy system might mean something totally different in another. So a hallucination here isn't just a tiny typo, it's a catastrophic error that ruins the entire interpretation of the research.
Section 2. Enter AlphaAgent, a skill-driven framework. Let's look at how the researchers actually solved this mess.
The secret sauce here is the concept of a skill contract. Basically, this is a semantic boundary that dictates exactly what an agent is allowed to read, what it can write, and what tools it can execute. And by laying down these strict boundaries, you preserve the evidential basis across the whole pipeline. If the system doesn't have explicit validated evidence inside its contract, it absolutely cannot fabricate mechanisms just to fill in a gap. It structurally isolates the failure modes.
Moving to Section 3, the retrieval skill, intent, and iteration. Let's zoom in on the first half of this decoupled system. AlphaAgent completely ditches the single-pass design for a bounded four-step loop. First, it takes a raw user request and rewrites it into a material-specific search intent. Second, it queries a massive curated index of over 300,000 papers from the journal citation reports for metallurgy. Third, it checks for an evidence gap, meaning, did the returned data actually cover the material system and property we care about? Finally, if the evidence isn't good enough, it reformulates the query and tries again. If it is good, it promotes that evidence to the next stage. It's constantly double-checking its own work. Let's ground this with a concrete example from the paper. Imagine a user throws in a vague query asking why the creep resistance of superalloys can't be judged by room temperature tensile strength alone. A standard RAG system, it's probably just going to search those exact words, pull up some broad generic summaries about high temperature strength, and totally miss the actual science.
But watch what the iterative retrieval does. After the first pass fails to find specific mechanistic details, AlphaAgent reformulates. It narrows the intent down to highly specific, keyword-dense microstructural terms, things like gamma prime precipitate rafting, dislocation climb, and diffusion-controlled deformation. It just keeps iterating until it finds a targeted evidence set that can actually support a mechanism-oriented answer.
Section 4. The generation skill. Sandboxed synthesis. Okay, the retrieval is validated. Now we hand off the data to a second, entirely separate agent.
This generation skill operates under incredibly strict rules. First off, it requires a pre-validated retrieval result. It is not allowed to do a cold start search. It essentially acts as a sandboxed reader. It parses the full-text PDFs, writes semantic drafts for each individual paper, and then synthesizes a cross-paper summary. Because it only ever receives validated material-specific evidence bundles, it is structurally impossible for this agent to cross-contaminate data or make up conclusions outside that evidence set. The generation step finally stops competing with the retrieval logic.
Section 5. Beating the baselines, AlphaAgent evaluation. So the architecture sounds great in theory, but does it actually work in practice? Let's check out the blind evaluation done by domain experts on 40 really complex material science questions.
Well, the numbers absolutely speak for themselves. The researchers pitted AlphaAgent against a baseline RAG system that used the exact same underlying LLM and document index, plus a standalone GPT 5.5 model. Look at these scores for deep analytical questions on a 1 to 5 scale. AlphaAgent pulled off an impressive 4.66. That dramatically outperforms the GPT 5.5 model at 4.05, and it completely crushes the matched baseline RAG system, which scored a pretty dismal 2.67.
Let's slice those numbers a bit further into specific dimensions. Here we're comparing AlphaAgent against baseline RAG for mechanistic depth and credibility boundary. AlphaAgent scored a 4.60 in mechanistic depth versus the baseline's 2.10. And this next one is huge, tracking credibility boundaries, which basically means knowing when the evidence actually stops and the AI should stop talking. AlphaAgent scored a 4.85 there against the baseline's 2.65. Separating retrieval and generation literally forces the model to respect data contracts, which prevents it from presenting speculative connections as established facts.
Section 6. The architectural takeaway. Deploy skill contracts. Let's distill all of this down. What does this mean for the AI systems you might be building or deploying right now?
Here are your actionable takeaways if you want to replace monolithic messes with explicit auditable skill contracts. 1. Audit your pipelines for task collision. If a single chain is doing both evidence retrieval and synthesis, you need to split it up. 2. Implement iterative query rewriting as a pre-processing step so you can actually narrow search intent. 3. Isolate your retrieval skill in a read-only environment. And 4. Sandbox the generation skill with strict output formatting rules. That way it can only synthesize exactly what's been provided to it.
So I want to leave you with a provocative question to really make you rethink your own workflows. Does your current AI architecture suffer from task collision? Because as AlphaAgent just proved, when you're dealing with complex, multivariable environments like scientific literature, structural discipline, and explicit skill contracts will consistently beat pure model scaling every single time. Thanks for joining me on this explainer, and I really hope this helps you build smarter, much more reliable AI systems moving forward.